Today, the most misleading metric in the battery industry is stack pressure. When a startup claims a breakthrough battery with 800 cycles and 90% capacity retention, they are lying by omission. What they almost never disclose is that this battery was tested inside a steel frame, clamped tightly under a hydraulic press, applying between 60 and 100 megapascals of pressure. To put that into perspective, 60 megapascals is roughly equivalent to the pressure experienced at the bottom of the ocean, 6,000 meters below the surface. Why is this pressure necessary? In liquid batteries, the electrolyte wets the electrode surfaces, filling every microscopic void to ensure perfect ionic contact. In solid-state batteries, you have two rigid materials, the cathode and the solid electrolyte, attempting to touch each other. At the microscopic level, they resemble rugged mountain ranges. Without external force to flatten these peaks and force atomic-level contact, interfacial resistance skyrockets. Ions simply cannot jump across air gaps. A commercial electric vehicle chassis cannot withstand 60 megapascals of pressure. The maximum pressure a standard battery pack can realistically apply using foam pads and steel straps is only about 0.1 to 0.3 megapascals. That represents a 500-fold gap between the physical conditions required for the battery to function and the physical conditions a car can actually provide. If you remove that miracle battery from the hydraulic press and place it into a vehicle operating at 0.2 megapascals, the contact resistance immediately increases by 2 orders of magnitude. The cell delaminates, voltage collapses, and the battery fails within 50 charge-discharge cycles. Startups fail because they are trying to integrate a laboratory experiment that requires industrial clamping force into a vehicle that demands lightweight and flexibility. We were promised a ceramic shield that would prevent explosions. Instead, we were given a ceramic sieve. Why do these unbreakable batteries still short-circuit? The core value proposition of solid-state batteries lies in the ability to use a lithium metal anode. This offers a theoretical capacity of 3,860 mAh per gram, 10 times higher than graphite. The theory is simple. A hard ceramic electrolyte should physically block lithium dendrites from penetrating and causing short circuits. That theory is fundamentally wrong. It fails because of a parameter known as critical current density. To compete with Tesla superchargers or vehicles like the Hyundai Ioniq 5, a battery must accept charging current densities above 5 milliamperes per square centimeter, enabling charging times of 15 to 20 minutes. However, most sulfide and oxide-based solid electrolytes under development today exhibit critical current density limits of only 1.0 to 1.5 milliamperes per square centimeter at room temperature. Here is the verifiable truth. When high current is forced through these materials, lithium deposition occurs faster than diffusion can accommodate. Pressure builds up at the interface. Contrary to marketing claims, dendrites do not need to be harder than ceramic to break it. They simply grow through grain boundaries, the microscopic seams between crystals, or propagate through pre-existing microcracks. The so-called solid barrier is not a wall. It behaves more like a sieve. When dendrites penetrate along grain boundaries and reach the cathode, the battery short circuits. Startups conceal this by testing at low current densities, charging over 3 hours instead of 15 minutes, or by heating the cell to 60 degrees Celsius to soften the lithium. But try telling consumers they must preheat their vehicle for an hour before fast charging. That is not realistic. What happens when you force an object that expands by 300% inside a concrete box that cannot move? It destroys itself. A battery is a living, breathing organism. During charging, ions flood into the anode, causing it to swell. In conventional batteries, graphite expands by about 10%. The liquid electrolyte flows around this expansion like water around a moving ship. It adapts effortlessly. Solid-state batteries are not forgiving. They use high-capacity anodes like silicon, which expands by 300%, or lithium metal, which represents infinite expansion as the layer grows from 0 to tens of microns. The solid electrolyte is rigid. It cannot stretch. As the anode expands violently, it creates massive shear stress at the interface. It is like trying to inflate a balloon inside a block of cement. Something has to give. Usually what gives is the interface itself. The layers physically tear apart, causing delamination. Once they separate, the ionic pathway is broken. This creates dead zones in the battery. The current is then forced to funnel through the remaining contact points, creating hotspots that accelerate failure. This is why a solid-state cell might look great for the first 50 cycles, while the glue is fresh but suffers mechanical suicide by cycle 200. No amount of chemistry can fix a fundamental mechanical incompatibility. Imagine trying to wrap a sheet of glass thinner than a human hair around a spool at 80 kilometers per hour. Welcome to the solid-state production line. This is where the economics die. The lithium-ion industry is built on the roll-to-roll process. Giant machines coat dry and wind electrode sheets at speeds of 60 to 80 meters per minute. It is a high-speed, high-tension process. To beat current batteries in energy density, the solid electrolyte layer must be aggressively thin, under 30 micrometers. If it is thicker, the heavy ceramic weight cancels out any energy gains. At 30 micrometers, ceramic oxides like LLZO are as fragile as a soap bubble made of glass. You cannot run them through a high-speed wender. They shatter. Startups are forced to abandon roll-to-roll and use sheet stacking methods, picking and placing fragile sheets one by one. This slows production speed down to 1 to 5 meters per minute. That is a 20 times reduction in throughput. Lower throughput means you need 20 times more factory floor space and 20 times more machines to produce the same number of batteries. The depreciation costs alone destroy the profit margin before the factory even opens. If I offered you a Toyota Corolla that cost as much as a Ferrari, but you had to keep it in a heated garage, and it died after 30,000 miles, would you buy it? The final nail in the coffin is the bill of materials. Even if the physics were solved, the chemistry is financially toxic. The most promising solid-state candidates are sulfide-based electrolytes because they are softer than oxides. However, they require lithium sulfide as a precursor. Lithium sulfide is a nightmare. It reacts with moisture in the air to generate hydrogen sulfide, a gas that is very toxic. Because of this toxicity, you cannot manufacture this type of battery in a conventional factory. You need dry rooms with dew points below -60 degrees Celsius and an inert argon atmosphere. The current price of high-purity lithium sulfide is approximately $2,000 per kilogram. The target price required for economic viability is below $50 per kilogram. Automakers are currently purchasing LFP batteries at around $70 per kilowatt hour. Solid-state battery startups constrained by exotic materials and slow manufacturing processes are projecting first-generation production costs of $600 to $800 per kilowatt hour.